All right. Thank you all for coming. Judging by the attendance today, good luck on whatever other exam you have this week, not this class. All right. So this week we have our third midterm exam review. So that's going to be Friday. So normal situation. So that's the 21st. 2 p.m. and the room is 2 doors down, SCC 103. All right, so that's going to be, as we have had before for midterms, 20 questions. If you want to go over them beforehand, that's great. If not, I'll go through them that day, obviously, and it will be recorded. So that's going to be happening this week in addition to our regular classes. And then just as a preview of what's coming next week, so the plan is this week we'll finish Chapter 9, all the course material that you guys will get for this course. And then next week will be the first parts of the final exam review. So Tuesday and Thursday of next week, when we would be having class, we're going to be doing that. So the final exam will be broken up into 3 parts. It is longer, and that way we don't have to spend too long on it on any given one day. And everything will be able to finish up easier that way. So that's as long as we get through everything this week, which is the plan. Before I get into today's course material, this is sort of the time of year when a lot of people wonder, like, what is my grade, or what grade could I possibly get, depending on the last 2 exams. And so this is just a little bit of information about, first of all, how to calculate your grade, and a little bit also about what the likely outcomes are. Now, obviously, with one more midterm and a final exam, those are worth 54% of your grade. There's a lot that that can happen to your grade, for the good or for the bad, in the last few weeks of the semester. But what I did is I went back to, again, spring 2019, which is a really big section, so it a lot of statistical noise gets washed out because of that. And so if you kind of calculate your grade now, in 2019, the average student's final grade was about 2% lower than their grade after the second exam. So on average, most people don't change a lot between now and the final. The first 2 exams are a pretty good sample size for how you're likely to do. And 75% of students, there's a big range within that 2% average, but 75% of students had their grade changed by no more than 9%. So 9% in our scale is approximately a letter grade. So in general, wherever you are now, it's not likely that you're going to have your grade go up or down by more than a letter grade. It's not impossible because of, again, 54% is a lot of big part of your grade still coming up. But for most students, where you are now is not going to be too different than where you end up. But improvements here and there are certainly possible. Now that leads me to, how do you actually calculate what is the maximum grade that I can get? And so basically the first thing you would do is you would figure out how many points you've already earned in the course. So you're going to just take your 2 numerical exam scores, 20 points maximum for each of them, add them together. And then the only thing that's a little bit tricky about this is you have to scale your homework score out of 6. And so you would have to we drop your 2 lowest, so you would take your 10 highest homework scores as of this point, and then average them out, and then set the average to 6. So basically take the average and divide by 2 is a way to think about that. And then also same with the bonus points. For that, you just take the average of those. So that's the trickiest part of this, but you just have to make sure your homework score is out of 6 points total out of all the average scores. And we have 2 more assignments left, but at this point, especially since we drop your 2 lowest, people's homework scores are not going to change really much at all the last 2 weeks. I mean, you should certainly still do them, and especially if you've missed homework assignments previously for whatever reason, you should definitely do the last ones to get as many points as possible, but it's not going to be a huge change in your grade at this point. So once you get that total, that's the number of points that you've earned so far, then we still have 54 left. So you just add 54 to that, and that would be the maximum grade you can get. Now that, of course, requires that you get perfect scores on the third midterm and the final, which is not impossible but not likely, of course. That's the maximum. And then if we want to figure out the same story with just the final exam left, you just add 34 if you've taken all 3 exams. And again, homework scores and bonuses can change a little bit over the next 2 weeks, but not likely enough to affect your actual grade. So really, it's the exam scores that are going to matter. So if anybody has questions about how to do this calculation or where you stand in particular, we can definitely talk about that. I'm not allowed to do grade discussions in detail over email. It's like FERPA academic privacy sort of rule. So if you want to talk about these things, you have to do it in person, ideally. But it's not too hard of a calculation the way we do our grading scale to figure out where you stand currently and where you can end up depending on your last 2 exam scores. So that's something that people always are wondering about, and this is a little bit of information about how to do that and also sort of how people's grades changed last semester at this point in the course, which in general was not very much. All right, what we're going to finish up, I guess any questions on that? Yeah.
Is the material we're going to cover right now part of the 30%?
The first 3 slides were just to finish up the practice problems from last time will be, yes. And then after that, it'll all be final exam material. So I'll make that clear when we get to it. Anything else? All right, so these are the last 3 example problems we had on phase diagrams. I had a bunch of them set up last time, didn't get through all of them. So we'll finish those. The phase diagrams is the last material that will be on the 3rd midterm. There'll be 1 question on it. Everything else we covered today will only be covered on the final. All right, so we had a lot of questions last time where we were just identifying specific points on a phase diagram, which phase or phases of matter is present, where's a triple point, critical point, things like that. The other types of problems that we sometimes have is where you're starting in one point and then changing the conditions and figuring out which phase changes occur as you do that. So here we have a situation where a researcher starts with a substance at 0.2 atmospheres and 100 Kelvin, and then increases the pressure to 2 atmospheres while maintaining a constant temperature. Which of the following lists the phases that will be encountered during this process? So when we do this type of problem, we figure out where the starting point is and find it on the graph. So 0.2 atmospheres and 100 Kelvin is there. And so where we're starting, we have to keep in mind where we're starting first. So this is going to be solid on the left, liquid in the middle, gas on the right. So we're actually starting in the gas phase. So really with that, if we trust ourselves to get that part right, we could already identify choice D as the right answer because that's the only one that starts in the gas phase. Now we want to make sure the rest of it is correct, or sometimes it won't be that easy to distinguish. So let's figure out what happens. We're going to just raise the pressure up to 2 atmospheres. We're going to go all the way up to here. And so what we do is as we cross and go up, once we get to this point here, we're going to cross into the solid phase. So we're going to go gas to solid. Once we get to 0.4 atmospheres, we're going to progress through the solid phase all the way up. But then before we get to the final pressure right about there at 1.6 atmospheres, we're going to cross back into the liquid phase. So we're going to go gas to solid to liquid. So we're going to go through all 3 phases in this process, starting down here, increasing the pressure, which is just a vertical transition through this diagram. And then you're going to end up in the liquid phase. So start with gas, solid, then liquid. So that would be choice D, which is the only one that starts with gas, even has the right starting point, but it does go in the correct order for that. All right, any questions on that? So when you're reading problems like this, sometimes it'll be vertical or horizontal. Sometimes you'll go sort of diagonal, but you just figure out your starting and ending points and then decide which phases you go through as you get to that. So it's just a little bit more involved in the last ones. Now the other thing that we can answer from phase diagrams that we talked about last time are the relative densities of the solid and liquid phases, and that's going to be determined by the slope of the solid liquid line. So solid, liquid, gas is always helpful to remember where those are. This line here that I've highlighted is the solid liquid line, and whether that's a positive or negative slope tells you the relative densities. Now instead of just memorizing which one is which, just think about what's happening. So if we start here, kind of like we did in the last problem, to be honest, you start here in the solid phase, and as we increase the pressure, so when you increase the pressure, you're increasing the density of the substance. You're compacting it more and more. And so you're increasing the density of the substance as you increase the pressure, and then all of a sudden you cross into the liquid phase. That tells us the liquid is more dense than the solid, because when we compress the solid, it turns into a liquid. So liquid will be more dense than solid whenever you have this negative slope of your liquid-solid line. So choice B would be the correct one. Liquid has a higher density than the solid. If the line was totally vertical, that's when they would be equal to each other, but that's not really the case for any real substance. So it's usually going to be one or the other, A or B, depending on the slope of that line. Okay, questions on that? All right, our last phase diagram problem is what is the vapor pressure of this substance at 250 Kelvin? So we can read vapor pressure off by just we just follow the liquid gas line. So vapor pressure is going to be, again, when we have the pressure of the liquid is equal to atmospheric pressure, and that's going to follow this liquid gas line. That's where those two phases are sort of coexisting with each other. So we follow the liquid gas line until we get to 250 Kelvin, and then that pressure reading is going to correspond to the vapor pressure. So we go to 250 Kelvin along the liquid gas line, read it back to the y-axis. It's a little bit above 1.2 atmospheres. Again, these graphs are not usually very precise, so we're not going to be able to get really exact with this, but somewhere around 1.3 atmospheres, let's say, or 1.25 if you want to be exact. So again, if it's multiple choice, pick the answer that's closest. These will typically be multiple choice questions on the test. So pick the one that's closest, so somewhere around 1.3, because that's where the liquid gas line, that's the corresponding pressure at the temperature of 250 Kelvin when we follow that. Okay, so that value does give us what the vapor pressure would be at any given temperature as we follow this line between the liquid and gas phases. All right, any questions? Okay, so that's the end of midterm 3 material. So it's the first 4 sections, I believe, of chapter 9 if you're following along with the book. And it's pretty simple to divide because it ends with phase diagrams. Anything that has to do with solids, structures of solids that we're going to start today is only going to be covered on the final exam. And of course, that'll be obvious once you go through the exam review as well. All right, so what we're going to cover for the rest of the entire course at this point are going to be structures and properties of solids. So we've talked about gases in chapter 8, liquids a lot for the first part of this chapter. Now we're on to the last phase of matter, which is solids. And again, everything we're doing here is going to be pure substances. So we're not talking about mixtures or anything like that at this point. Just pure substances, the different types of solids you can have, and a little bit about their structures. So there's essentially 2 major categories of solid materials. So one is called amorphous, one is called crystalline. And so an amorphous solid is a solid that has no regular structure. So a way to think about an amorphous solid is, you know how in a liquid we have the molecules are kind of just randomly arranged and tumbling around each other. Just freeze that in time. So the molecules are no longer moving when they're in the solid phase, or not moving very much, but the molecules are just sort of randomly piled onto each other, or the atoms, if they make up, if it's atomic structure. They're just kind of randomly piled in, no real regular structure to it. So amorphous solids are solids that have no regular structure. And so whatever makes up that solid, the atoms or the molecules, or I guess ions if it's an ionic compound, although amorphous ionic compounds are not particularly common, but whatever makes up that solid are arranged randomly. So it's, again, kind of like a liquid, except those atoms and molecules are no longer moving in the solid phase. They're just sort of stuck in place, but randomly arranged. So the classic example of an amorphous solid, which you've encountered in your everyday life, is glass. So glass is mostly made up of silicon dioxide. I mean, there's different types of glasses and different things you can dope into it, but mostly SiO2 for glass, similar to sand. But it's an amorphous form of that substance, so there's no regular arrangement of the atoms in that. But we're not going to really talk anything else about amorphous solids in this class. You have to know what they are, and I gave you the definition here. But because they have irregular structure, because there's no clear way of defining what the structure is, there's not a whole lot else we can say about them. So we're going to really stop there and just give you the definition. What we are going to talk about a lot today, and also next time, a different category, are crystalline solids. And so these are going to be solids where the components are arranged in a highly regular periodic fashion, basically a repeating arrangement of all the atoms or molecules. And so that's what a crystalline solid is. And so then when you have a crystalline solid, to be able to define what the structure of that is, there's 2 key terms that are associated with it. One is lattice. So a lattice is typically a three-dimensional. In our case, it could be two-dimensional as well. You can have two-dimensional lattices, but we're only talking about three-dimensional lattices, which is a 3D system of points where each point represents an atom or a molecule in the crystal. And so basically when you have these crystalline solids, whatever components make them up are going to repeat in sort of a regular pattern in all directions, and that's called a lattice, with that sort of pattern of points that you get. One way to visualize a lattice, this is a little bit probably the harder part to understand to some extent, what a lattice is. But pretty much it's every patterned carpet, for example, or every patterned floor, with a regular pattern, would be an example of a two-dimensional lattice. I guess the floor in here kind of works, although the little color pieces are kind of small, so they're hard to see unless you're like looking right at it. But you have this sort of alternating pattern of, I guess is like, what is it, mustard and ketchup color? I don't know, this is a terrible color, but like brown and yellow or whatever you want to call those colors, they're sort of the regular pattern that just repeats over and over again, and in this case in 2 dimensions. We're going to talk about the same thing in 3 dimensions where the lattice points go in all 3 directions, but that's basically what a lattice is. It's a repeating set of points, and in a chemistry sense, those points are going to be atoms or molecules that make up that structure. So it's a 3-dimensional system of points where in chemistry terms, each point represents an atom or a molecule in the crystal. Now, the reality is that truly understanding what a lattice is requires a pretty high level, knowledge of symmetry, which we don't cover in general chemistry for obvious reasons. It's something you won't cover until your very advanced courses if you stay in the chemistry major or other related subjects. So the way that we're going to define these lattices and these crystal structures are in terms of what's called the unit cell, which is still a very useful way to think about it. So the unit cell is the smallest repeating unit in a crystal, where you can generate the whole crystal by just translating that unit cell. So a simple way to think about this is, stacking blocks, taking, in our case, they're all going to be cube-shaped blocks that represent the unit cell, and just stacking those in all 3 directions. And so the unit cell is the block, and then the crystal structure is made up by stacking those blocks in all 3 directions. And so the unit cell is the piece of the crystal that you just translate in all 3 directions or stack in all 3 directions to give you the extended structure. And so the unit cell is what we call the smallest repeating unit in a crystal. This is not the most precise definition, but for our purposes it works. And basically what you do is you generate the lattice by stacking this or translating the unit cell in all 3 directions. So the types that we will talk about in detail for unit cells are all going to be cubic, as I said, and basically, each corner or side or edge, different combinations of the different positions on that cube are going to have atoms or ions located there, and then that cube will be translated in all 3 directions to generate the extended solid that we would be talking about. Yeah.
So if you say you have table salt, would the unit cell, I guess, would that just be sodium chloride, or would it just be one?
Well, we'll talk about sodium chloride next time, but basically when you have something like sodium chloride, the lattice points are the sodium and chloride ions that basically repeat in all 3 directions. The unit cell is going to be a cube, and as we'll see, you're going to have chloride ions on the corners and the faces of the cube. And then in little pockets in between those chloride ions within the cube, on the edges and inside, you're going to have the sodium ions. So it is a repeating unit, but the unit cell itself would be a cube that has in total 4 of each ion in it. So sometimes more than just 1 of each, but yeah, exactly. When you have an ionic compound, that's what happens. The ions repeat in all directions. Yeah.
So it would be correct to say the unit cells are all identical in structure?
Yeah, so when you have a perfect crystal, a pure crystalline substance, it's going to have millions and billions and however many unit cells that are all the same, just repeating in all directions. I mean, keep in mind, the unit cell is on the atomic scale. Usually, as we'll talk about, a few atoms or a few ions in the cell. And then when you have even just a small piece of sodium, that's going to be, 10 to the 20 whatever. So it's going to repeat, many, many, many times in all directions. Exactly right. All right, anything else? All right. But before we get into structures, let's talk about some different types of crystalline solids categorized in terms of their composition, so what makes them up. So there's three major types. The first one we'll talk about, and we'll talk about a specific category today, are called atomic solids. And so as the name suggests, it's just made up of one type of atom. In other words, it's a form of an element. So any element that forms a crystalline solid would be classified as an atomic solid because there's only one type of atom in the structure. So examples would be, the one that's pictured here is diamond, which we'll talk a little bit about. Diamond has tetrahedral carbon atoms, and then they repeat in all directions. And the type that we're also going to talk about a lot today are most metals. So, mercury, as we talked about, is a liquid, but any other metal that exists as a solid and as a crystalline solid, which is true for most of them, or at least in some conditions they would be crystalline, they would form atomic solids, just that metal atom repeating in all directions. So diamond and most metals are examples of atomic solids. The other type we'll talk about next time, and already came up in one of the questions today, was ionic solids. And so here you have positive and negative ions that sort of repeat as lattice points. And pretty much any ionic compound you can imagine would have this type of categorization. We'll talk about pretty simple ones like sodium chloride, zinc sulfide, magnesium chloride. So these binary ionic compounds typically have structures that are easily defined and at least appropriate for a general chemistry audience. So we'll talk about those. And then the last one, which we won't talk a lot about, but we will mention some of their properties later on, we won't talk about their structures in too much detail, are molecular solids. So this would be a solid form of a covalent compound. Where the lattice points are the molecules. And another important point about molecular solids is to sort of relate back to things we learned earlier in this chapter. In a molecular solid, all the molecules are held in a regular pattern, and the way that they're held in place is by those intermolecular forces that we already talked about. So classic examples of molecular solids, the one that's shown here is solid water, which we call ice. So that's where the water molecules are arranged into this sort of hexagonal structure in all directions. And then if you have a lot of the polyatomic elements that exist as solids, so P4, S8, I2, those diatomic or polyatomic elements that have discrete molecules in the solid phase, they're going to be classified as molecular solids because they're held together by London dispersion forces for each of the individual molecules, either P4, S8, I2, and so on. So those are the types based on the composition, what makes them up. We'll have a summary of this later on before we wrap this all up. I don't know if it's today or next time, but essentially identifying what type of solid is mostly just going to be determined by the composition, what type of compound it is. Is it an element? Is it ionic compound? Is it a covalent compound? That's going to sort of dictate whether it's classified in any of these three ways. All right. The first type we're going to talk about in detail are metals. And to understand how metal atoms are held together in a regular crystal structure, we first have to talk about what's called metallic bonding. So this is sort of a distinct category of bonding. We talked about covalent and ionic early in the course, and that's kind of the two major types we had considered all throughout. But this is a third type of bonding that's a little bit different in terms of how it works. And it's kind of hard to draw it or visualize it, but I'll do the best here. So basically, it's what the model for metallic bonding is called the electron C model. And so if you think back to things we learned way back in the early parts of the course, probably back in chapter 2, if you go to metals that are on the left side of the periodic table, they tend to have low ionization energies. It's easy to remove electrons from them, and that's why they form cations whenever they make ionic compounds. And so in metal elements, you have the outer electrons, the valence electrons, are held pretty loosely in the structure. They're not really tightly bound to the atom like they are in the main group elements. And so what that means is that when you arrange metal atoms together into a regular pattern in a crystalline solid, what you can almost think about is that all those valence electrons are basically just loosely floating around the whole structure. They're not bound to one atom, or they're not shared between two atoms. They're just floating around all over the place in the whole structure. And so what you can kind of draw that as, and again, it's not a particularly satisfying drawing, but it's the best we can do. If you have, let's say, a group 1A metal, first column of the periodic table, we know that those metals all have one valence electron. And so basically what you can think about the metallic structure being composed of is they all have these loosely held valence electrons, one of them per metal. So you're going to have basically, cations all arranged in a regular array like this. And then what I'm going to draw here is sort of just a yellow smear is going to be all those valence electrons holding those cations together. So one valence electron per atom, but they're all kind of just floating around in the structure. So sometimes this crashes the program when I do this, so I'll be careful. If I just start going crazy with scribbling, it doesn't like it. But essentially you have this yellow smear here is just representing all the valence electrons, one per atom, but just loosely held, floating around the whole structure, kind of holding it together like a glue. And it's not that the electrons are held to one atom or shared between two atoms. They're just freely moving around. So what I'm drawing here in yellow is what we call the sea of electrons. So whenever you see that term sea of electrons, that means metallic bonding with loosely held valence electrons just sort of floating around the whole structure. And then if we had a group 2A metal, very similar story, but now in group 2A, which is the second column, we know that there's two valence electrons. And so each atom is going to have two valence electrons that are floating around, and so you're going to be sort of formalize these as 2+ cations, and then the two valence electrons are going to be all delocalized and floating around. And again, this sea of electrons, this sort of diffuse, mobile kind of arrangement of electrons where there's no real structure to the electrons, no real localization of any type. It's just loosely floating around between all the atoms and holding everything together. So in a metal in any sort of metallic element arranged in this way, all the valence electrons are loosely held and delocalized. Now this metallic bonding also happens in the liquid phase for metals. The only difference is that in the liquid phase, the atoms are able to move around, but they're still in contact with each other, and they're still sort of held together by that sea of electrons. In the solid phase, the atoms are just held really tightly, and they're just not really moving, and the sea of electrons holds everything that way. So whenever you're in a condensed phase, liquid or solid for metals, you're going to have this type of bonding. So that's also true in things like mercury, which are metallic liquids. Okay, so that's what metallic bonding sort of looks like. And another key part of this last part of this course is to understand then how the structure, the properties, the bonding, whatever the case may be, in all of these different types of solids, how that influences their physical properties. And so there's some important properties of metals that are related to this electron sea model of the bonding. So the first is, let's talk about the melting points of metals. In a relative sense, they have moderate to high melting points. So as we'll talk about, they're not as high as ionic compounds. Ionic compounds have really high melting points, but they tend to be higher than most of the non-metal substances on the right side of the periodic table. Covalent compounds or most non-metal elements have lower melting points. But what's important to also realize is now we can predict how the melting point changes as we go through the periodic table on the left side with the metals. So the first is if we go across a period. So basically what we're essentially talking about here, if we move, it's a little bit harder with the transition metals, they're not as predictable. If we just move from group 1 to group 2, so lithium compared to beryllium, or sodium compared to magnesium, just moving left to right across the two main group elements columns here on the left, what happens to the melting point? Well, as we talked about, when you go from group 1 to group 2, you're going to have in group 1, just one valence electron per atom holding everything together. In group 2, there's going to be 2 valence electrons per atom holding everything together. So the more electrons that are holding things together, the more tightly they're going to be held. So we would expect the melting point to increase as we go from group 1 to group 2, because the metals are held more tightly by the 2 valence electrons versus 1. So when you go across the period, the melting point increases. Again, particularly from group 1 to group 2, it's not as predictable in transition metals, so we won't ask you about that. But we're talking about for main group metals here, melting point increases as you go across left to right. And that's because you have more valence electrons, and so the atoms are more strongly attracted to each other, held in place more strongly. Because when you want to melt something, you have to take those regular, rigid sort of structures and break everything up so that the atoms can start moving around. So you need to break a lot of those forces of attraction. Now if we go down a group, so if we go from, let's say, down a column, which would be like lithium down to cesium, or beryllium down to barium, going top to bottom in a column of the periodic table, this one is maybe not as intuitive, but what happens in this case is that the melting point decreases. And basically that's because as you go down, you have larger ions. And so that sea of electrons is not able to get as close to the positive charge, if you will. It's more diffuse. And so that leads to weaker attractions. And this kind of parallels what we talked about with ionization energy. Ionization energy is for a single atom, of course, not for a solid structure with electron C. But as you go down the period, the outer electrons are held more loosely, and so the same thing is true in the solid phase. You have more loosely held outer electrons, so everything is kind of just held together in not as tight of a fashion, so that makes it easier to melt the substance. Now if we talk about the boiling point of metals, which we rarely do because you don't typically see metals in the gas phase, and that's because metals have very high boiling points. And the reason is because if you're going to melt a substance, you have to break up some of those attractions to get the atoms to start moving around, but they're still in contact with each other. The metallic bonding is still intact. But if you want to boil the substance, you have to break all the metallic bonds and completely separate the atoms from each other. So that requires, really for any substance, that's going to require more energy, and particularly for metals, where you have to break all the metal-metal bonds to do this, all the metallic bonds. And so it's very high to, the boiling points of metals are very high because it's difficult for those, formal, the cations, the inner core, and the valence electrons that are holding them together. It's difficult to break those up completely. If we're going to boil something, we have to break all of the forces holding it together, and so of course that's much harder to do than just disrupting some of those forces to liquefy it. So boiling points for metals are very high because these metallic bonds are pretty strong and holding everything together, and you have to separate all of those for that to occur. Now in addition to phase change properties, there's a couple of other physical properties of metals that are related to this electron C model for the bonding. So one are called mechanical properties. Mechanical properties is basically how hard something is, how flexible something is, all those things that related to its sort of macroscopic structure and macroscopic behavior in terms of its strength and things like that. So the key mechanical property of metals that distinguishes them from really any other substance is that they're malleable. So malleable is just a fancy word for bendable. So metals can be bent in most cases without breaking them. And the reason for this is that even though you have this electron C that's sort of holding everything together, but there is some flexibility to it because the electrons are not tightly held in place between two atoms. They're floating around the whole structure, so you can bend it without sort of disrupting that altogether. So the metal ions are not too tightly held in place because the electron clouds are diffuse and sort of delocalized and moving around everywhere, so you don't have any real penalty for rearranging those atoms to some extent. And so basically these metal ions can slide through the electron C and that allows the structure to be distorted without completely destroying it. So it is possible to bend metals, and that's related to their type of bonding that they have. And then the big one that we're probably all familiar with from metals is that they're good conductors of electricity. All the wiring that we use in the whole world basically is made up of metals. And same with, they're also good thermal conductors, meaning that the heat transfers through them very easily. And the reason for that is because of the mobile, loosely held electrons. That's especially obvious for electroconductivity, where you have these electrons that are freely floating around. And so if you're going to conduct charge through the material, it requires that the electrons move through freely. And that's, of course, true when you have this metallic bonding that we already talked about. So metals are good conductors in the solid or liquid state because they have these mobile electrons that can easily move around the structure. And that, electrical conductivity in particular, it relies on those mobile electrons to be able to have that, okay? So those are some key properties of metals that relate to this metallic bonding. So again, in Chapter 9, as you've already seen, we're not going to go into a ton of depth on any one topic, but there's just a lot of little things, and this is sort of some relationships between the bonding that we have in metals and some of their key properties. So any questions on that? All right. Now, the big thing we're going to have to get through today that's probably going to be a little bit unfamiliar for just about all of you are the structures of crystalline solids, how to define them, and some things about them that are related to how the atoms are arranged. So first we're going to give just a really brief background on how we determine these structures. This is not something that you're likely to be tested on in this course, but I think it's helpful just to know, when we start talking about unit cells that make up the different types of structures that we have, how do we figure out what those are? Is that just something we're making up, or is it, there's an experimental way to do this? And the experimental method that we use is called X-ray diffraction. So we talked about diffraction just a little bit in this course, which is basically the idea that when you have electromagnetic radiation or electrons, because they have wave behavior as well, as we talked about, if they go through a regular array of points, they're going to sort of split off in all directions, and that's called diffraction. And in a crystal, those atoms are the points that are arranged in a regular way, and the wavelength of X-rays are similar to the spacing between the atoms in the structure, and so that allows that diffraction to occur. Crystals won't typically diffract light very well because the wavelength of light is 400, 800 nanometers, and the spacing in crystals are about a tenth of a nanometer or so. It's a lot smaller than that. So if you try to just shine light in a crystal, nothing really is going to happen, or nothing useful is going to happen for determining the structure. But with X-rays, which have really short wavelengths that are similar to how the atoms are spaced, you're going to get diffraction as they go through. So the X-rays are going to scatter off the atoms. And that's essentially what X-ray diffraction happens. So when that occurs, when you have two beams or more, or splitting off into more than two directions as it goes through, you can have either constructive interference or destructive interference of the scattered waves. So constructive interference is when two waves line up with each other, and you get an increase in amplitude as the two scattered waves interact. And then destructive interference is when the crest of one wave lines up with the trough of another, where they're out of phase with each other. And then when you add them and they interfere with each other, you get basically no signal at all as a result. And so the way that the experiment works then, and we have this instrumentation down in SR1, just right over, right next to us here. You take a crystal, you shine an X-ray beam on it, and then those X-ray beams are going to scatter off of the crystal. The old school way of doing it was having the X-ray beams scatter onto photographic plates, and then you read off where the X-rays hit sort of manually. Now it's all computerized, and they use these fancy detectors that just collect the X-rays and translate them into a digital image for you. So it's a lot faster and a lot easier now. But basically, where you see these spots, this is called a diffraction pattern. The spots are where that constructive interference occurs. And so you get this pattern of spots. and the pattern of spots, through a lot of, mathematical magic that we're not going to cover in this class, that pattern of spots then translates to how the atoms are arranged in the structure. And we'll give a little bit of a background on that on the next slide, but again, you don't need to know all these details. This is mostly just for informational purposes. And because this is a topic that I really like, so I'm going to cover it whether you guys like it or not. So those spots on the diffraction pattern are where the X-rays constructively interfere. And the angles at which that occurs and the spacing between those spots is directly related then to how the atoms are arranged in the structure. And the other thing you do, which is not obvious here, is you rotate the crystal around in all directions. So you don't just collect one diffraction pattern and call it a day. You take the crystal and you rotate it in all directions, and every time you rotate it, then the pattern of spots changes, and all that put together gives you that entire three-dimensional structure. So again, a lot of math that goes into it, all computerized now for us, thankfully. Because it used to be the case that getting one crystal structure in the early days of this technique would have taken years. I mean, people had entire PhD thesis that was just determining the structure of one compound. Now we can do this in sometimes even a few hours or less. So it's gotten a lot faster now because of all the automation, all the computerized stuff that not only collects the data much faster, but then also processes it and does all the math for us, so we don't have to sit down and do it ourselves. And so the way this kind of works a little bit more quantitatively then is when you have a crystal, you have these regular arrangement of atoms all repeating each other in all directions, and so you can define two-dimensional planes of atoms as you cut slices through that crystal. And so then what occurs is that an X-ray, if it's at the right angle, it's going to diffract off of one plane, and then at the other, then it's going to also diffract off a different plane. And basically, the angle that these are coming in at is going to determine the spacing between these planes, where you get this constructive interference. So what we're going to have here is lambda here is going to be, as it's always defined, as wavelength. So the X-ray has a characteristic wavelength. And then what we also have that's an important parameter here is this angle theta, which is called the angle of incidence. So we rotate the crystal relative to the X-ray source. Usually the X-ray source is stationary, and we just rotate the crystal relative to that, so that the X-rays are coming in at different angles relative to the planes in that crystal. And so that theta is the angle of incidence. And then d here is the distance between the planes of atoms. So we arrange, the atoms can be thought of as being two-dimensional planes as we cut slices through the three-dimensional overall structure. And so the distance between those we're going to abbreviate as d here. And then the equation that sort of relates all this together and allows the structure to be determined is called the Bragg equation. And the Bragg equation is basically n times lambda, some integer multiple of the wavelength, is equal to 2d sine theta. Where n is an integer. And so this is sort of the basis then of how these structures are determined. We measure the angles at which constructive interference occurs. We know the wavelength of the X-rays that we're using, and then from that we back out distances between the planes of atoms. And we do that over and over again in all different directions, get all these different distances, and then that allows us to piece together the three-dimensional structure. So I'm leaving out a lot of critical details, of course, but that's essentially how it works. Another cool fact about the Bragg equation is that it was developed by a father and son team. So there's two Braggs actually that were involved with this. I believe they won the Nobel Prize for this. I did things like play baseball with my dad, and Bragg and his son were winning Nobel Prizes together. So, different strokes for different folks, I guess. And so that's the Bragg equation. Again, you have to do it in all directions. There's a lot more complicated math that goes into really piecing together the final structure, but this is the essence of how it works. So again, that's mostly just background for you guys to know where these structures come from. The more important thing in this course is going to be how we define them. The types we're going to talk about in most detail are going to be cubic structures, where again, that means that the unit cell, the piece of the crystal that we just translate in all directions, that we just stack on top of each other over and over again to make the structure, is shaped like a cube. So within a cube, there's going to be 4 different places that you can put atoms in the cube. And different structures are going to have different combinations of these sites occupied that are going to give some different properties and different things about that. So one would be to put an atom right in the center of the cube, which we call the body center position. And then the other thing that we have to define for all these positions is not only where the atom is located, but how many different unit cells is it going to be shared between. Because again, in the whole structure, we're taking these cubes and we're stacking them in all directions. So if an atom is on the edge of the unit cell, it's going to be shared by 2 or more unit cells, and then it's only going to count as a fraction of an atom for that individual cell. However, if we have an atom at the body center, it's not going to be shared by alternating unit cells because it's completely inside the unit cell. And so in this case, a body-centered atom is going to be not shared at all, and we will count it as one whole atom. Because part of what we have to be able to do to understand and to predict some things about these structures is count how many atoms are in each unit cell. And so if you have an atom completely inside of the cell, whether it's right in the center or it could be, off to one side, but it's completely enclosed by that cube, it counts as one total atom because it belongs entirely to that unit cell. Now, another position that we often have atoms located is right on the center of one of the square faces of the cube. We call that a face center position. And then in this case, as you can probably visualize, imagine stacking these blocks all in all directions. Any face center position is going to be shared by 2 unit cells. Because as we stack the blocks together, the 2 faces come together, and so any atom that's right on that face is going to be shared by 1 cell on this side, 1 cell on the other side. So it's shared by 2. So a face-centered atom is going to be shared by 2 unit cells. And so when we're counting how many atoms are in that one cell, we count it as 1/2 if it's in the face center position. So this will count as 1/2 of an atom if it's in a face center. Another position we'll see, although not until we start talking about ionic compounds next time, is you can put atoms along the edge of a unit cell as well. So right along one of the edges of the square. So we call these just edge positions. The names are not terribly complicated. And in this case, again, you have to imagine stacking these cubes in all 3 directions. This is going to be shared by how many unit cells? Close? 4. Because you're going to have 1 next to it and then the 2 in front of it as well. That would all be sharing the same edge. So there's going to be a total of 4 cubes that share 1 edge. If you have cube-shaped blocks at home, or if you have, siblings that play with them, that could be helpful in this part of the course. But basically, if you stack all 4 cubes together, they're all going to share 1 edge. And so they're shared by 4 if they're in the edge position, which means you count them as 1/4 for that specific unit cell. I think visualizing these things is helpful as long as you know the outcome. Edge counts as 1/4, face counts as 1/2. That's really going to get you what you need for the problems you'll do. But being able to picture it is, of course, helpful. And then finally, the last position, which is pretty much going to always be occupied in the different structures we talk about, is the corner positions. So corners are going to be shared by 8 because you're going to have the 4 that would share a common edge, and then 4 more on top of that all share that same corner. So if you stack 8 cubes together, they all come together at the corner, 4 below, 4 above, and so that would be shared by 8 unit cells, meaning it counts as 1/8. So when we're counting atoms inside the unit cell, if you have atoms in the corners, they count as 1/8 each for that unit cell. So that's how we're going to count the atoms in the different structures that we have. And so now what we're going to go through is the 3 major cubic structure types that we would have for metals, for basically any element that would occupy these structures. Ionic compounds are coming next, and they're sort of based on these same structures to some extent, but we're going to just talk about the structures of metals today and the 3 possibilities that we have for cubic metal structures, the 3 most common ones anyway that we would have to be responsible for. And so the first one here is called the simple cubic structure. Now, I'm going to have a table at the end of today that kind of summarizes all the important information about these structures. So again, don't think all the details are important. It's just trying to help you understand things a little bit better for some of these things that I'll give you. But anyway, the first thing we're going to talk about is just what this looks like. And there's sort of two ways of picturing these structures. So one would be to take layers of atoms and then stack them on top of each other to generate these different structures. And the way that we would do that for the simple cubic structure is we're going to start with one layer of atoms. Now all of them are touching, or they're all as close together as they can be. But you can also see that the way they're stacked is just in straight rows. So you just have a straight row of atoms, another straight row right below that. So there's just these sort of straight rows of atoms. And then you just take those layers and just stack them directly on top of each other to make the simple cubic structure. For most students, sort of visualizing or understanding this layer stacking is not the most intuitive or easiest way to picture the structure, so that may or may not work for you. But the important thing is to understand sort of the shape then of the cube that results. And so when you have a simple cubic structure, each unit cell is a cube, and what you have is one atom at each corner, and that's all you have. So the simple cubic structure, this would be one unit cell for the simple cubic structure. And then if we take that one unit cell and stack it in all directions, we get the extended structure, where again, I'll try to highlight one in here. You have all of these cubes here. I think I did that right. So that'd be one cube, and then you're just taking that same cube and stacking it in all directions. Okay? So I didn't highlight it perfectly, but you get the idea. You're taking this one cube and stacking it in all directions. But this would be the unit cell here. That's the part that you should probably understand the most. And a simple cubic unit cell, you just have one atom in each corner of the cube, and that's it. So that's the most basic one. The other way to visualize this, usually it's easier to kind of see what's going on if you put little spaces between each atom, but in reality they're all sort of touching each other and occupying as much volume as possible. So this is kind of what that looks like with the atoms shown at full size. Not as intuitive, but basically what you can see is that all the atoms are occupying the corners and they're touching in all directions. They're as close to each other as they can be. There's not these big empty spaces like this picture would sort of lead you to believe. Okay, but this is the easier one for sort of understanding where all the atoms are. All right, so simple cubic structure is just a cube with an atom at each corner, nothing more than that. Now, the other thing that we can define for each of these structures is sort of the last number we're going to give here is the important one, but some relationships between the dimensions of the cube and the sizes of the atoms that make up the cube, and also then what defines eventually what's called a packing efficiency. What percentage of the volume is occupied by the atoms in that crystal? Because as you can see, there's some empty spaces in there, even when we show them in their full size. So what percentage of that volume is occupied by the atoms themselves? Well, that just really becomes a geometry problem more than a chemistry problem. So let's talk about some of the geometric aspects of this structure. Again, not all these details are going to be important for you guys. The packing efficiencies will be, at least in a relative sense, like which one is most dense, which one is least dense, and so on. We don't need to probably know the exact numbers necessarily, but let's just go through some geometric aspects of it. So if we take one face of the cube, that's what I'm showing here is one face of the cube, what we're going to have is an atom in each corner, as we said. And so what we would define then is the length of one side is going to be called A here, abbreviated as A. And then the atomic radius is going to be defined as R. So the radius of the atom that makes up that structure will be defined as R. So you have this relationship then between the length of the side and the atomic radius. And what we can clearly see here, because the atoms are touching along each side, the length of one side A is equal to 2 times the radius. We go 1 radius, 2 radiuses to get across the whole side. So that's the relationship in this structure between the length of a side and the atomic radius. Now what we also know is the volume of a cube, if you've taken geometry before, which I'm sure you all have, but maybe it's been a while, the volume of the cube is just the length of the side cubed for a cubic structure, so A cubed, or in alternative terms, 2r cubed, which is 8r cubed. All right, so that's going to be some relationships then between the atomic radius and the length of the side and the volume, all those things. Pretty simple for this simple cubic structure because everything is just touching right along the corners and along the sides. Now what we also have is we can count how many atoms or how many spheres there are per unit cell using the counting rules that we introduced a little bit ago. So in this structure here we have, again it's probably easier to see back up here, we have 8 corners in a cube and all 8 of them are occupied. So we have eight corners. Each one counts as 1/8 because they're shared by 8 unit cells, as we talked about. So that's the only positions we have in this case are corners. So in total, this structure has 1 atom per unit cell. It's really 8 1/8ths per unit cell because you have each corner occupied counting as 1/8, but total is 1. 8 times 1/8. And that's going to be an important number for us to understand for all these different structures as well. How many atoms per unit cell or how many spheres if you're talking about it more generally. So there's 1. And then what we also know from geometry is that the volume of a sphere, there's 1 in the unit cell, and the volume of a sphere is 4/3 pi r cubed. So the total volume occupied by the atoms is just going to be 4/3 pi r cubed, where r is that same atomic radius. And so now finally what we can do is we can define what's called a packing efficiency, which is the volume that the atoms or the spheres occupy over the total volume of the unit cell. So what we do is we take the volume of the spheres, divide it by the volume of the cube, and then packing efficiencies are typically expressed as percentages, so we multiply by 100. So what we found is that there's 1 sphere in the unit cell which has a volume of 4/3 pi r cubed. The volume of the cube itself was given as 8r cubed from the geometric arguments we presented earlier. So if you divide these two, the radiuses cancel out. It comes out to pi over 6 times 100, which expressed numerically is 52.4%. So in the simple cubic structure, just over 50% of the volume of the unit cell is occupied by the atoms. The rest is all empty space. Okay, so that's the number that we get for simple cubic. All right, again, the important parts are counting the atoms and then at least understanding in a relative sense what these packing efficiencies come out. The rest is useful background information, but not necessarily things you have to fully internalize. So any questions on this so far? All right, so now we're going to do the same thing for 2 other types of structures. And so the next one we're going to talk about is called body-centered. Geometrically, this ends up being a lot more complicated, but in terms of visualizing the structure, it's not too bad. So in a body-centered cubic structure, let's talk about how we would generate it from layers. So first is we're going to place atoms in a layer, but we're going to have spaces in between them this time. All right, so when we're generating a body-centered cubic structure, we can't have all the atoms touching anymore. We have to leave a space in between. And the reason is that we're going to make a second layer that's identical. I'm just showing it in red so you can see it better. And we're going to put that on top of the spaces in the first layer. So again, we have these little gaps here, and now we're going to stack atoms on top of those gaps in the second layer. All right, so that's how we stack. The second layer is right over the spaces in the first layer. And then we stack the third layer so that it eclipses the first layer. So basically we just repeat that pattern A, B, A, B, A, B, where we're just slipping the layers into the gaps of the previous layer. So the third layer is right on top of the first, but separated by the intermediate layer between them. And so again, this sort of, stacking picture is not always satisfying for everybody. So that may not work for you so well, but what we can see then is in terms of what the unit cell looks like, it's relatively simple. In a body-centered cubic structure, as the name suggests, you have all 8 corners, which I'll put little blue dots on, and then right in the middle here, should probably use a different color than red because it's hard to see red on top of red. Right in the middle here, you have one right in the center of the cube. So it's not too different than simple cubic. We just place one more in the center of the cube. Now what that does, though, is you can see because we're forcing an atom into the center, the atoms that are in the corners no longer touch along each side. We basically had to force open that volume a little bit to fit the atom in the middle, and so now there's little, the atoms in the corners, they're still there, but they're not touching along the sides anymore. We have this one additional one in the center. Okay, so that's what the body-centered cubic looks like. Again, not too difficult to visualize. It's just a cube with one more right in the middle. Now, the geometry of this one ends up being a bit more complicated. So what we're going to do in this case is we're going to go through the cube diagonal. So we're going to, for example, start here, go through the center of the cube, and then come out on the opposite corner all the way across the whole cube. So basically bottom corner to top, bottom left to top right, and so on. And so that's what we're going through. One corner of the cube all the way to the opposite corner. So as we go through that diagonal, what we're going to come across are basically three atoms. One that's in the corner, one that's in the center, and then another one that's in the opposite corner. So that's how, as we're going through, and you can kind of see that here. We go through this atom that's in the corner, we go through the atom that's in the center, and then we come out through the atom that's in the opposite corner. So that's how we're going to be traveling through that diagonal. So let's talk about the geometric aspects of this. The first is that the length of a cube diagonal, again, just a geometric argument, the diameter squared is equal to the sum of the sides squared, which is just a squared plus a squared plus a squared. We're still using a to define the length of one side of that cube. And so that means the diameter is going to be given by a square root of 3. Okay, so whatever the length of the side is, multiplied by square root of 3, that's the length of the diagonal of the cube. Not diameter, diagonal. The length of a side in this case, this is going to be the part that's a little bit trickier in terms of the radius. So the diagonal is equal to a square root of 3. And as we said, as we go through that diagonal, maybe easier to see up here, as we go through the diagonal, we're going to go through one corner atom, the center atom, and then the next corner atom. So a total of 4r. We have one radius for the corner atom, the whole diameter of the center atom, and then another radius for the other corner atom. So a total of 4r as we travel through that diagonal from the bottom corner to the next top corner. So that's going to give us 4r. And that means the relationship then is that A is equal to 4r over square root of 3. Again, don't worry about learning all these. We're just building up the packing efficiency. Now, the important part for us to be able to do is counting the number of atoms or spheres in the unit cell. So again, flipping back to here is going to be useful. So we still have all 8 corners occupied. And just like before, we have 8 corners, and they count as 1/8 each. But we also have one atom in the center now, as we're showing here, the one that I've highlighted in green up here, one in the center, that's completely inside the unit cell, so that counts as one full atom for that unit cell. So we have one in the center, which counts as a whole atom, that's the body-centered position. Anything that's inside the unit cell counts as a full atom. And so in total now, the body-centered cubic cell has 2 atoms in the unit cell. Really 8 1/8 plus 1, which is a total of 2, okay? So you have 2 atoms per unit cell, and that means the volume of the atoms, or the volume of the spheres, then is going to be 2 times 4/3 pi r cubed, or 8/3 pi r cubed. All right, and so now we have everything we need to define the packing efficiency, because we have the volume of the spheres, we have the length of the side, and if we cube that, that's the volume of the cube, and so we just have to divide the 2. So the spheres are going to be 8/3 pi r cubed, 2 times 4/3 pi r cubed. The volume of the cube is going to be 4r over radical 3, whole thing cubed. And we multiply that by 100. So that means we get 8/3 pi over 4 over square root of 3 cubed, which numerically comes out to 68%. So we can see by putting that one atom in the center, by forcing some of that empty space to be occupied, we've increased the packing efficiency. So the body-centered cubic structure now has 68% of its volume occupied versus only 52% for the simple cubic. So again, deriving this, not terribly important, I'm just giving you that so you know where it comes from. But this number here, this is more efficient, more dense, if you will, than the first structure we talked about. So that's body-centered cubic. All right, any questions on that? Yeah.
That pi is in the numerator, correct? In the 8/3.
Yeah. So it should be 8/3 pi. I'll try to do that better. All right. So that's how we get the packing efficiency for that one, and that's, again, counting the atoms is going to be particularly important for you guys. All right, the last type, which is going to be important for ionic compounds also, is called face-centered cubic. So this one looks the most complicated, but again, if we break it down into simple elements, it's not too bad. So in face-centered cubic, the packing arrangement is probably the most complicated, and again, you don't necessarily have to fully understand this, although you should have a little bit of an idea. So in face-centered cubic, we start with what's called a close packed layer. So imagine that you have a bunch of marbles and you're trying to arrange them as close to each other as they can be. This is the way you would do it. You would start with one row where they're all touching, and then you would stagger the next one into the next row, basically filling the gaps in the first row. So that gets them as close together as possible. Another way to think about this is if you look at one atom here, it's going to be surrounded by 6 others. And that's the closest that you can arrange spheres to each other. So you start with what's called a close packed layer. That's where we're putting the layers as close together as possible, all the atoms in the layer. And then the way that we stack these is called either ABC or ABCA. And so essentially what you have is, we're going to call this yellow layer is going to be called, the bottom layer, we'll call that A. And then what you'll notice is that each of these layers here, let me highlight one of these in red. In each of these layers you have these little triangular divots in between 3 atoms. And you're going to put the second layer right on top of those divots. So that layer, which I'm showing in blue here, is going to be called the B layer. And it goes in those divots. And then the third layer is going to go on top of the divots in the second layer. So again, now we see that this green layer here, shown in hollow spheres here and solid spheres over here, goes on top of the triangles of the second blue layer. So each of these layers has these little triangular divots between, and the third layer goes on top of there, so we call that C, the C layer. And then we just start repeating after that. So it's basically now the fourth layer is going to eclipse the first. So 1, 2, 3, 4. So every 4 layers are identical. So those two are going to be identical to each other. That's A again. And then the ones in between are called BC. So what we call this is ABC, or sometimes ABCA packing. And all that means is that we stagger the layers 3 times before we start repeating, and then we just do that pattern over and over again. Now this is difficult to visualize because the cube, as it turns out, you have to take these stacked layers and kind of turn them on their side a little bit. So actually the stacking goes through the diagonal of the cube, not like directly along the edges or anything like that. So again, showing it in yellow here, if we call yellow A, I kind of made it probably confuse you guys by accident. Yellow was A, and we'll call yellow the second yellow A. So basically you have an A here, an A here. We call the blue one B and the green one C. So that's they're kind of again stacked along the diagonal of the cube. So it's hard to visualize the connection between those, but you should understand, at least at a basic level, that ABC packing, taking close packed layers and stacking them staggering 3 times and then repeating itself, is how we generate this structure. Now the unit cell, which is what is most important, again, it looks pretty complicated, but and then if anything, the bottom picture is easier to visualize in this case. But what you have is, again, I'll show these in blue, all 8 corners are occupied. So in all these cubic structures you have an atom in every corner. And then what you also have in the face-centered cubic, and that's where it gets its name from, is that right at the middle of each face of the cube is another atom. So I'm going to show those, I guess I should do them in green because again red doesn't show up very well here. And then in green I'm going to show all the face-centered positions. 1, 2, 3, 4, 5, 6. There's 6 faces in a cube, and all 6 of those have an atom right at the center. Again, that kind of maybe works better here, where you have all 8 corners, and then right in the center of each face, these 3 are particularly easy to see in this view, you have an atom right in the center there. So that's what face-centered cubic looks like. 8 corners plus all the faces have an atom on them. All right, so for this structure here, the geometry is not as bad as the last one, because what we can do is we can just go along a face diagonal here. And as we go through the face diagonal, we're going to go through a corner atom, the face-centered atom, which is 2r, and then another corner atom, which is another r. So this time we're just looking at the length of a face diagonal, not the cube diagonal. So the face diagonal, if this is, again, the side length is a. From geometry, a squared plus a squared equals the face diagonal squared. So the face diagonal is a radical 2. I'm using the same letter D here, which don't let that confuse you. We're talking about now just the diagonal of one two-dimensional square face of the cube. So a radical 2 is the length of a diagonal. And then, so to relate that then to the radius, this diagonal a radical 2 is equal to 4 times r. Because as we go through a face, we go through 4 radiuses. 1 for the corner, 2r for the center atom, 1 more for the other corner. So a radical 2 is 4r, which means the relationship here is that a is equal to 4r over square root of 2, which can be written more simply as 2 radical 2r. Okay, so this is the relationship between the side length a and the atomic radius r for this structure. And then counting the spheres, again, this is probably the most important part for us in understanding these structures. What we have in this structure are all 8 corners occupied. Again, we show that up here, and that's going to be true for all the cubic structures. 8 corner atoms, counting as 1/8 each, same argument as before. Plus we have all the faces occupied. So there's 6 faces in a cube. 1, 2, 3, plus the 3 others that are obscured, or you can see them all up here in green. There's 6 faces. And then we said that the face center positions all count as 1/2 because they're shared by 2 unit cells. So we have 8 1/8 plus 6 times 1/2 for the faces. So in total, there's going to be 4 atoms in the unit cell for the face center cubic structure. All right, and so the volume of the spheres then is going to be now 4 times 4/3 pi r cubed. Each sphere has a volume of 4/3 pi r cubed. There's 4 of them in the whole unit cell, and so the total is going to be 16/3 pi r cubed. And then same approach as last time. If we wanted to calculate the packing efficiency, we take the volume of the spheres divided by the volume of the cube, which is just this cubed. And so we get 16/3 pi r cubed divided by 2 radical 2r, sorry, the whole thing cubed, times 100. And I won't try to simplify that at all. We'll just give it numerically here directly as 74%. Okay, so this is the most efficient cubic packing that we can have. So we went in that order, from simple cubic, which was 52%, body centered was 68%, and now if we go to face centered, that's the most efficient cubic packing we can have. 74% of the total volume is occupied by the atoms. The other 26% would be empty space. All right, so that's going to be the structures of those 3 cubes. Any last questions on those? All right, the last thing that I'll introduce, which we're not going to talk about in great detail because it is harder to visualize, are the hexagonal close packed structure. So in a hexagonal close packed structure, what you basically have is the same close packed layers, but now instead of doing ABC packing, we're going to just do AB packing. So you're going to basically stack one layer, stack the other ones in the divot, and then you're going to immediately eclipse the first layer with the third layer. So it's now just an AB packing where we just stagger it once, and then we start repeating that pattern over and over again. So that's A and that's B, and then so basically this would be A, B, A, B. So it's called AB packing. So the hexagonal close packed structure is generated by or ABA packing. Now technically the number of the unit cell for a hexagonal structure can be just thought of as this sort of rhomboid. It's not really a cube, it's a 4-sided structure, but now you don't have right angles anymore. Or you can take 6 of these and arrange them into an actual hexagon, which is maybe an easier way to visualize it. So if we look at this hexagonal structure up here, and we want to count the number of atoms. This one is not intuitive, so don't worry about the how we count them. But basically, you have 12 atoms in this structure that are shared by 6 unit cells, and then you have 3 that are individual, and then you have 2 at the top. These 2 top ones here are shared by 2 unit cells. So again, don't worry about how we got this number, because I don't have the best picture here to show that. But this is going to come out to a total of 6 atoms per unit cell. But the important thing for hexagonal packing, which is really probably the only main thing you have to know about it, is that the packing efficiency is exactly the same as cubic close packing, which is 74%. So if you do this close pack stacking, where you take these close pack layers and then stack them either AB or ABC, they generate different unit cells. If you do AB packing, you get hexagonal. If you do ABC, you get the face-centered cubic that we just talked about. But both of them have identical packing efficiencies of 74%. So the main thing you need to know about hexagonal structures is that they're generated from the same layers as the previous one. Different structure, but same packing efficiency. Yeah.
What do the colors represent then, like A and B?
They're the different layers. We're just showing them so that you can easily see them from each other. So we're calling here the yellow layer is A, so that's the first layer of atoms. B is shown in blue. That we're going to put that second layer right on top of the triangular divots in the first layer. And then for AB packing, the third layer goes directly on top of the first layer. So these yellow spheres, which are basically arranged right on top of the other ones. And so the ones that are shown in the same color are basically stacked directly on top of each other, although they always have at least one layer in between. All right, so that's hexagonal packing, but again, not a lot to say about that. The last thing we'll do before I'll give the summary next time as a bit of a review, is defining what's called the coordination number. So the coordination number is the number of nearest neighbors. Basically, if you look at one atom in a structure, how many other atoms is it touching? Is it directly next to? And that's also going to be something that's different for each of these structures. So the number of other atoms that one atom in a structure is touching. So to define coordination number, it's usually easiest, for most of these structures, it's going to be easiest to just look at the layers. That's where the layers can be somewhat helpful. So if we look at face-centered cubic, or sorry, simple cubic first, we said that the layer, this is what the whole structure looks like, but each layer was going to be arranged like this. So if we look at this atom here that I've marked in X, it's going to have 4 atoms that surround it in the same layer. And then if we stack these layers, there's going to be 1 atom directly on top of it from the next layer, and 1 atom directly below it from the layer below it. So there's these 4 in the same plane, plus 1 above, 1 below. And so what that means is the coordination number, abbreviated as Cn, is equal to 6 for simple cubic. Or if we look at this atom here in the structure, see if I can get this right. It's surrounded by this one, this one, this one, and this one. Those 4, 1 above, 1 below. I'll put an X on that one so you see this one I'm talking about. Okay, so those are the 6. This is harder to see, but 4 atoms in the same plane that are directly next to it, 1 above, 1 directly below. So coordination number of 6 if we're talking about simple cubic. For body-centered cubic, which was the next one we talked about, this is probably the easiest one to visualize, because we just have to look at the unicell here, focus on the one that's in the center, and then see how many atoms are around it. Well, it's just surrounded by the 8 corners. 1, 2, 3, 4, 5, 6, 7, 8. So the coordination number for body-centered cubic is equal to 8. So just focus on the center one. All atoms have the same coordination number. It's not that the corner ones are different. It's just I'm not showing the whole structure. But if you just look at the one that's in the center, 8 nearest neighbors clearly from the picture. The one that's most complicated is going to be the face-centered cubic, which again we have to go back to the layers here. So if I look at this atom here, in the B layer as it was called before, we have 6 atoms in the same layer that surround it. And then if you look at the layer that's directly below it, remember that it sits in the sort of the triangle between 3 atoms below it. So those 3 yellow atoms, 7, 8, 9, are going to be also nearest neighbors. And then you'd also have 3 above it. So again, we're talking about this atom here. This is the atom that we're talking about, the one that I put an X through. And then in the layer above it, you also have 3 more. So that's going to be 10, 11, 12. So 6 in the same layer, 3 above, 3 below, because it sits in the divot between 3 neighboring atoms on the next layers. And so the total coordination number then for this would be 12. So what we can see then is that the coordination number sort of tracks with the packing efficiency. Simple cubic is least efficient, and the atoms have the fewest nearest neighbors. This one in the middle, this one the highest. So what we'll start with next time is a summary of the key things you need to know. So this will fill in this table here that gives you the important information for each of these structure types that you should definitely remember. And then we'll move on into ionic compounds, which are roughly related to these but have some different features.